Hello guys, so welcome back to my channel, and today we're going to talk about the wave equation. But before we get into the wave equation, we are going to check the solution to the question I gave to you the last time to try. So in this question, we're supposed to classify, and we're supposed to classify the second order PDE. And then if you write that the coefficients as a symmetric matrix, that's what you have. Your A11 is going to be x squared, your A12 is going to be x, your A22 is going to be y squared. And what you realize is that your delta becomes x squared multiplying y squared minus 1. So considering this means that the classification of the PDE is going to depend on the value of x and y, right? So considering the values of x and y, I shaded the regions for you, and the red lines are the values of y's and x, which will make the PDE parabolic. So when y is equal to plus or minus 1, you can see that this part goes to 0, making the entire thing 0. And when x is 0, the entire thing goes to 0. So you have a parabolic PDE. For the yellow region and the yellow line, you realize that y is in between -1 and 1, which makes this side always negative, right? And if that is always negative, you know that x squared is always going to be positive. So you're going to have a negative, you're going to have a negative value for the delta, which is going to give you a hyperbolic PDE. And similarly, the blue part is where you have an elliptic PDE. Okay, so now let's move straight into the wave equation. So there is a proof for the wave equation, how to come about how to derive the wave equation. There's a derivation for that, but in this video I'm not going to do that because it's kind of long and other people have already done that. So if you're really interested in that, I would suggest you watch other videos to find that. But this is basically what the wave equation looks like. And just a few remarks. We have the wave equation with dissipation. That's the first one. So that's this dissipative term. And the coil spring, and the Ku is actually the restoring force when you pull the string or when you try to stretch the string, and also compress the string. And the last one is the force-driven string. Okay, yeah. So those are just remarks. We're just going to talk about the wave equation. Okay, the basic one. That's the UTT being equal to CUXX. I'm gonna see how we can solve that. Give me a moment. Okay, so the wave equation can be written as UTT minus C squared UXX being equal to 0. Okay, and then right at the beginning of this entire PDE class, you remember I said we could write this as del T squared minus C squared del X squared, right? So the del T is representing G equals 0. So the del T, when I put in U here, I'm going to have the derivative of U with respect to T, the second derivative of U with respect to T. I hope you get what I mean. Yeah. So that's what we have. And then you can see that this is going to be a difference of 2 squares. So I'm going to have something like del T minus C del X, del T plus C del X, G equals 0. Okay, so what comes to mind, you can see some kind of transport equations here, like you have a product of transport equations in quotes, right? Yeah, so that should come into mind. So what we are going to do here is to do a transformation from the xt coordinate to a different coordinates. Okay, so we are going to do a transformation from the xt coordinate to maybe a c and eta coordinate. So I'm going to call it c x minus ct because we are thinking of transport equations here, right? And eta to be x plus ct. Okay. So anytime we do a change of coordinate, what do? We do a derivative of u with respect to t, since that is what we have, and that is going to be the derivative of u with respect to c, then the derivative of c with respect to t, right? Plus the derivative of u with respect to eta, oops, my bad, respect to eta, multiplying the derivative of eta with respect to t, okay? So there's going to be u c multiplying, del c del t is going to be negative c, right? Then plus, you're going to have u eta del t is going to be minus, that's going to be c, right? So multiplying c, right? Yeah. So basically, let me put that in the normal terms. You're going to have c multiplying negative del u del c plus del u del eta, right? So this is your del u del t. Remember, we are changing coordinates from the xt to c and eta. So similarly, del u del x is going to be, del u del eta del x plus, c, then del u del eta del x. So you're going to have, del eta del x is going to be just 1. So I'm going to have del u del c plus del u del eta is just going to be del u del eta, and then del eta del x is also going to be 1 from this equation, right? So that's going to be del u del eta. Simple as that. Okay. So let me call this. So let me call this equation 1, equation 2, then equation 3. Okay. So you're gonna substitute these equations 2 and 3 into equation 1. Okay. Yes. So if we do that, we're going to have, so we substitute equation 2 and 3 into equation 1. Okay. So if we do that, we're going to have c squared multiplying del u del eta, del c del u del eta squared minus c squared del u del c plus del u del eta squared, and that should be equal to 0. Okay, because in equation 1 you have that being equal to 0. So del t here means del u del t, right? So del u del t squared, and we know what del u del t is. That is it. So you square that, you put that here, then you do the same thing for c squared del u del x, and that is going to give you that. So that's why we have this equation, right? Okay, so now let's move on. So what do? We can rewrite this as c squared, then I'm going to multiply this by, I'm going to try and expand the squares. I'm going to try and expand the brackets, okay? So that's going to be minus u, actually it's going to be squared because it's going to be squared, it's going to be a positive value. So it's going to be u eta squared plus, actually minus 2 u eta c eta, because it's going to be minus 2 del u del eta del u del c. Why do I always keep mixing that? So del u del c del u del eta, and that's going to be negative 2 del squared u del eta, or del c del eta, right? So that's why I have this minus 2 u c eta. Okay. So then plus del eta squared. So that's what we're doing. You do this, you apply the same thing to the next term. That's going to be c squared del c squared plus 2 del c eta plus del eta squared. I mean, that's it, okay? And that should be equal to, oh my god. Oh man, let me do this so that it becomes a bit simple. Del eta. Okay, then I can put my u here, and that should be equal to 0. Okay. All right, so we can see that this term is going to cancel that term, and this term is also going to cancel that term. Now, when you try and simplify, you're going to have negative 4 c squared del c eta u being equal to 0. So actually, the 4 goes away because, you're equating everything to 0. So the 4c squared, actually, the negative 4c squared goes to 0. And then you're going to have del c eta u being equal to 0, right? Yes. And what does that mean? It means that this is actually u eta the c eta is equal to 0, okay? And then we've seen this before. Anytime you try to, if you have a PDE in the form of, like, say, u, x, y equals 0, the solution was always given as, f of x plus a certain g of y. Remember that, right? So it means that the solution to this is going to be a function of c, u of eta, c eta is going to be, a function of c plus a function of eta. But what is c? We know c to be x minus ct and eta to be x plus ct. So it means that the solution in the original coordinates is going to be f of x minus ct plus g of x plus ct. Right? So anytime you're given a wave equation, all right, a wave equation with no, boundary conditions or initial conditions, the solution is a function of x minus ct, if you have a space variable and a time variable, plus g of the x plus ct. Okay, so we're going to see an example, and we're going to further continue with whatever we need to know. All right, so see you in the next video.